Good morning. Welcome everyone to the EasyPower Thursday webinar series. My name is Jim Chastain. I'm host for the webinar today. And we have a very popular topic and a fairly large attendance registered for this session, so welcome to all. And as we are in the habit of doing, we'd like to start the presentation before we introduce our guest speaker with some poll questions, and we would appreciate your participating. If nothing else, for just to advise or kind of illustrate where the audience stands with perspective on the topic, but also today's are a little fun in really testing ourselves on what our current knowledge base is. So again, welcome everyone for attending. And here's our poll questions. And the first one is, what OSHA regulations cover grounding requirements? Let's see how you do on this one. I, for one, didn't do that well on the list of questions, so I'm not participating. All right. Looks like we have a quorum. Here's how people have weighed in. It looks like we have a heavy favorite as far as the audience is concerned. Thank you. So our next question is, does NFPA 70E cover grounding? And if so, where? And I, for one, consider myself a fairly heavy proponent of NFPA 70E. It looks like we do have some authorities in the audience. I'm glad to see that. Appreciate your participation. Okay, here's how everyone weighed in on this one. And we'll see how Jim will cover the answers in the presentation, so I'm not going to try to get into the details. The third question is, what is the ASTM standard covering personal ground protection? And I, for one, was kind of lost on this one, so I'm looking forward to the details of the presentation. So give it your best shot. You can't do any worse than I did. All right, that looks pretty good. Here's how folks weighed in on this one. Again, it looks like we have some favorites. All right. The fourth question, what rating in the OSHA regulations is best to size the personal protective ground to? So the verbiage is a little bit misconstrued, but once you see the answer selection, it makes more sense. I think I even got this one right, so I'm looking forward to some experts coming from the audience. All right, looks like we have a quorum to this one. Here's how the results stack up. All right. And then the last question, what is the shortest cable length ASTM recommends? And again, this one was, for me, a bit of a guess. Looks like we have a fairly good distribution here. And here how folks have weighed in on this answer. All right. Again, thank you for participating. And now I'd like to introduce our guest speaker. Jim White is a principal member of the NFPA 70E, NFPA 70B, NFPA 70 CMP 13, and ASTM F18 committees, and has for a fair amount of time been considered a thought leader in the industry. And with that, I'd like to introduce Mr. Jim White, our guest speaker.
Okay. First of all, thank you all for attending this presentation. Second of all, I apologize for my voice. I live in Texas. I am being pummeled and battered by mountain cedar pollen, which I'm very allergic to. So it's got me hued-eyed. So I apologize for that. If there's something you don't understand, you will get a copy, a PDF copy of the slides so you can back it up. So let's begin. First thing I have to do is tell you that I represent the National Electrical Testing Association on several committees. I give you my opinion. I cannot give you the official position. You would have to write to the organizations and get the official position, just to be clear. So anything I say has to be considered personal opinion. So first thing we're going to talk about are OSHA regulations. And typically we don't start out with 29 CFR. You say 1910-269 or 1910-333. Now, a lot of these I'm going to look at quickly. Others I'm going to take a little time. But you'll notice in 269M, it says they shall be installed as required by paragraph N, and that's the next section. And here it says, for the employee to work lines or equipment as de-energized, then they have to be grounded as specified in this paragraph. Equipotential zones, speak a little bit going in. I don't have time to take it up a lot, but they have to be arranged in such locations in such a way that you're provided an equipotential zone. And that means that as long as you're within the equipotential zone, you are safe. If you take your foot and you leave the equipotential zone, say goodbye to your family. You aren't going to be there anymore. The next section, N4, says protective grounding equipment shall be capable of conducting the maximum fault current that could flow at the point of grounding for the time necessary to clear fault, and it can't be less than number 2 AWG copper. And we'll look at this a little more later. Grounds have to have a low impedance. They're designed with a low impedance. If they're connected correctly, they will have. And before any ground is installed, lines and equipment shall be tested and found absent of nominal voltage. Now, you could have an induced voltage. That is not what they're talking about. But be aware, if you're working in a substation, that ground has to go on quickly if there's an induced voltage so that it doesn't start arcing. The next two are very, very simple. Connect the ground connection first to the ground, and then you attach each phase. When you take it off, take off each phase, and the last one you take off is the ground connection. When work is performed on a cable location remote from the cable terminal, which could be a long cable, cable may not be grounded at the cable terminal if there's a possibility of hazardous transfer, the potential should a fault occur. In other words, they want you to go grounded on the other end. That grounds the whole cable. Grounds may be removed temporarily during tests. During the test procedure, the employee shall ensure that the employee uses insulating equipment. So you got to use insulated rubber gloves and is isolated from any hazards involved, and the employer shall institute any additional measures as may be necessary. And there's quite a few that you could fall into. Don't mean that intentionally. So we look at 333, which is your general voltage, your medium voltage, and it says stored electric energy which might endanger personnel. Now we're talking capacitors, we're talking any type of capacitive equipment. That could be a long power line. So they have to be discharged and high capacitive elements short-circuited and grounded. Overhead lines, if work is to be performed near overhead lines, the line shall be de-energized and grounded. So often what we have is static discharge, especially when you get into medium voltage, which is what this section considers. If any vehicle or mechanical equipment capable of having parts of its structure elevated, like a lift truck or something of that nature, near energized overhead lines, is intentionally grounded, employees working on the ground near the point of grounding may not stand at the grounding location. And we're going to talk about different ways to be near personal protective grounding locations. Then we'll talk about NFPA 70E. I go off the new edition, and you'll find most of the information concerning personal protective grounding is in Article 120. It's in Section 120.5. Now, I've highlighted some important points that I want you to be aware of. Establishing and verifying an electrically safe ground condition shall include the following steps. 1, determine all possible sources of electrical supply to the equipment. That could be something that you believe is de-energized and is still energized. So you have to check applicable, up-to-date drawings, diagrams, and identification tags. And you have to be careful. This is a big problem. After properly interrupting a load current, open the disconnecting device for each source. Wherever possible, visually verify that all blades of any disconnecting device are fully open, or that the draw-out circuit breakers are withdrawn to the test or fully. And again, we're talking primarily medium voltage here. Release stored energy. You have to take a grounding stick and be sure that any energy that may be stored by capacitors or inductors, anything of that nature, is relieved. Block or relieve stored non-electrical energy so they cannot unintentionally be energized by such devices. Well, if you do de-energize those devices, that's very slim, but things happen. Apply lockout tagout devices in accordance with documents and established procedure. You should have one, I hope. Use an adequately rated portable test instrument to test each phase conductor or circuit part to test for the absence of voltage. And then you test them phase to phase and phase to ground. Before and after each test, determine that the test instrument is operating satisfactorily. So you want to go back, you want to do a test on a known live object, circuit, whatever. Test your grounding, and then retest the equipment. Where the possibility of induced voltages or stored electrical energy exists, ground all circuit conductors and circuit parts before testing. You will remember if you don't do this. I guarantee I've done it. And I remember it well, and I never forgot it. Where it could be reasonably anticipated that the conductors or circuit parts being de-energized could contact other exposed energized conductors or circuit parts, apply temporary protective grounding equipment in accordance with the following. So temporary protective grounding equipment shall be placed at such locations and arranged in such a manner as to prevent each employee from being exposed to a shock hazard. So again, primarily we're looking at attaching the ground connection first, and then attaching grounding cable to each of the energized or de-energized lines. And the application of temporary protective grounding equipment shall be identified as part of the employee's job planning. A lot of people don't plan very well. Let me tell you, grounding is so important. Of course, again, it says just like OSHA, it has to be able to carry the maximum fault current. And for those of you who are not familiar with ASTM F850, look like a lot of people were, that's good. This is where all your grounding specifications are located. Temporary protective grounding equipment and connections shall have an impedance low enough to cause immediate operation of protective devices in the case of unintentional energizing. And if you do not have proper size grounds, they're going to fuse, which means they're going to melt. Then you don't have to worry about impedance because everybody's dead. So here's a shot of a well-constructed temporary personal protective grounding. And you'll notice you've got your ground connection and your three-phase connections. You've got your ferrules. You've got your connection points in the heads. All of these are rated to carry the maximum fault current, or they better be. So it protects against accidental re-energization, induced potentials, capacitor discharges, and static discharges. Static grounds, though, are a little different. They're typically lighter. They're not used as a personal protective ground. They prevent static buildup on tested equipment in the substation. And that static buildup could be for a nearby line, or it could be from a DC test that you did. So static grounds discharge all that. It should only be used when equipment is completely isolated and disconnected from power lines because they're not intended to carry fault current, and used only for testing purposes, of course. Personal protective grounds, on the other hand, must meet the requirements of ASTM F855. Each component must be sized to carry the maximum short didn't say that right, short circuit current for the amount of time needed to clear the fault. And again, that's everything. It must be designed, and this is important. A lot of people miss out on this. The ground clamp has to be designed to fit the type of ground it's going to be. Is it round? Is it flat? You know, you have different type of ground clamps designed for different types of grounds. This, by the way, is not a ground clamp. It's not a ground cable. It's called suicide. And this was actually found on a transformer that we were about to work on. It's incredible. Here's another example of suicide. Your car starts pretty good with them. Yeah. Well, guess what? They don't ground very well. So they just melted and they blew off when the ground was energized. The arc from this was enough to burn up the cubicle. Sometimes you gotta wonder. So let's size personal protective grounds according to ASTM 855. Now, this is not from 855. This is your base calculation. The short circuit current, which you have to know, is the base KVA of the transformer times 1,000 divided by the square root of 3 times the voltage, secondary voltage. That's not seconds, that's secondary. And then you divide that by the percent impedance divided by 100. I don't like long calculations. Most of this information you get off the data plate. As long as you know for full load current, That can be calculated easily. The impedance percent comes off the data plate. So here's an example. I have a 2500 kVA transformer. I got a 480 volt secondary, and my phase-to-phase impedance 5.5. Pretty regular transformer. Well, you take that information and you put it into your calculation, and you come up with 2,500,000 divided by 831. And I hope you have a calculator. So you come up with 3,007 full load current. Divide that. Now you notice I took that impedance and I turned it into a non-impedance number, 0.055. And I come up with 54,000. I would round that up to 55,000 myself, what I would do. That's my short circuit current. And that is what the ground has to carry it for. So then we slide over to the NFPA 855, NFPA, ASTM 855 table 1. And you notice I have two ratings. The withstand rating is the rating I want to choose. Because if I choose the withstand rating and the ground sees one shot of rated short circuit current, it can take another shot. If I go over to ultimate capacity, and I've seen people do this. Oh yeah, the ultimate capacity is blah, blah, blah thousands. Well, son, you better hope it only energized once, because I've seen them do more than once, because that's all this can handle. At the ultimate capacity rating, it's very likely it could fuse, which means no. This gives you an extra chance. This one is no chance. And then looking at the ultimate rating, you can see it's very high, 70,000. If I look at the withstand rating, I see it's quite a bit lower. So it's just a margin for error. And I have to put up two grounds that are the same size, same impedance, and the same length. That's the way to handle. Don't just do one and think it's good. So here's the definitions in ASTM F855. Ultimate capacity is expected that component damage may result. Wonder why? You're having an explosion there, pal. The component shall not be reused except in test situations, if there's anything left. The withstand rating, the protective ground shall be capable of passing a second test at the current after being cooled to ambient temperature. So at least you have some kind of chance here. And I always use the withstand rating. Cable impedance really has to be as low as you can make it. Longer cables have more impedance. That's why the NFPA, the ASTM F850, somebody shoot me. ASTM F855 tells you 10 foot. That's the shortest it should be. And what they don't say is in discussions I've had with the committee and with utility people who use personal protective grounds all the time for their lines, they say 20 feet is about all you can go. You go above 20 feet, the impedance really gets kind of nasty. And that's going to decrease the opacity and could risk someone being struck by it whipping. I know you've probably been on YouTube, seen a lot of short circuits on grounds and how they whip. You don't want to be there. OSHA says no smaller than number 2 AWG copper, not AWG aluminum, AWG copper. That's the law. So for a quarter second, looking at a 15 cycle, 250 milliseconds, which by the way is a quarter second, you can use one 250 kc mil, comes out to 54 thou, or you can use two 2-watt, and that comes out to 54 thou. And the chances of you hitting exactly the short circuit current are pretty slim. Usually it's quite a bit less, but make it as close as you can. Installation and removal. Always test for the absence of voltage first. And use the live dead live method. But even though you don't have nominal voltage, you can have induced voltages, which can be very dangerous levels, thousands of volts, but they don't have any current to them. But they don't need a lot of current at that voltage. Backfeeds. Seen this before where you get backfeeds on lines because somebody forgot to open a switch. And then automatic operation of the equipment by an automatic transfer switch. Those things have to be disabled. They have to be blocked out and locked out. Don't trust voltage detectors until they have been proven to work by re-verifying the absence of voltage. So you test live, you test the line to make sure it's dead, you test live, then as a last test, go back and recheck your line. Just a few seconds. Never tap a circuit using a static ground. I say it is old school stupidity. And let me tell you why. Here's a story. The guy at a steel plant was grinding out a transformer, and they kept their transformers for their reactors that melted the metal. We're talking super high current. So it was a 13/8 circuit. The transformers themselves were in separate rooms, separate vaults. I don't know why they built it like that, but they did. So they turned off the right transformer. You went into the wrong room, took a static ground, bumped an energized 13/8, and he suffered burns 98% of his body, 98%. And that guy did not die, but I don't know why. And he returned to work. Nice guy, by the way. Connect the ground side connection first, always first. And that will bleed off induced voltage to ground. Then use the proper type and size of ground clamp. And here's a good example. You know, would I bet my life on that? Well, I don't know. I'm not really that stupid. I think I might do something else. This is an actual picture of utility lineman. With grounds, you only use a live line tool, which he's doing, for attaching or disconnecting ground. Never use your hand. If it hits fault current, adios, muchachos, and never contact the ground in any location of the cable or anything else while you're placing the grounds onto the equipment. The fact of the matter is, the ground cable is not protected against the voltage. It's protected against being damaged. So act like the voltage is energized as soon as you strap it in place. And if you want a day at the beach, please go to the beach. I won't join you, but you can take pictures. Remember, ground should be between 10 and 20 feet in length. Absolutely locate them So they will not contact personnel. And when I say train cable, if they're too long, wrap it around a post or something that will give it some support so it doesn't whip out. I know on YouTube, if you look at videos of grounds being shorted, man, those things whip. Never coil ground cables. That's an inductor. It's going to blow it up. Do not use ground cables with T-handles. Those are static ground. And wear proper PPE. And let me tell you, being on the 70E committee, I am the man that loves PPE. Wear it, love it, put your name on it. I don't care. This is good. If it is not grounded, it's not dead. That was on a utility substation. I like the way they do things. So when we look at grounds, we take a metal conductor and we insert it into the ground, usually with a hammer, if you're like anybody else. And what that does is create ground earth resistance, earth resistance. And the earth resistance is considered to be equal width. So as it spreads out, if you look at these circles, or half circles, you can see that they're getting bigger and bigger. So your highest resistance is right here, and as you go away, you get lower resistance. Well, you insert current through your ground bar. And one of the things that happens here, we can have touch or step potential. And this is showing how if the ground isn't good on this device, but is good on your shoes, it's going to flow through your heart. Hopefully, your friends will come to your funeral. Step potential, big problem in a substation. You'll notice it's going up through his legs, through his hip, and back down. So those are the two types of potentials you can encounter having bad grounds. Again, this is a good ground. It's got all the right parts. They're all rated. As a matter of fact, at one of the ASTM meetings I went to, the F855, the manufacturers are saying that a lot of people take components from different manufacturers and assemble them, and they recommended that that not happen because the different parts are not designed to go together with each other. And that surprised me. I've never heard that before. But they were pretty stringent about it. And they're not trying to sell ground cables. They do that anyways. Here's a bad ground cable. You can see that it's got corrosion. The connection itself is not good. There's a lot of things going on that's not good with it. Here's my favorite, a ball stud. ASTM 855 has done testing, has found that ball studs give you the lowest impedance of any type of ground you can use. Now, if that doesn't wake you up and make you write a note, I don't know what does. But these are the best things you can use for grounding. And you get them a different configuration. They actually have extended ground studs now, where it has to be longer. They have longer ones. And what I really like about them is that you can put an insulating cover over them and don't have any problem with metal clad switchgear. Good stuff. Now, here's one that's got some corrosion. You can see it darkening in here. It's starting to corrode. The impedance of it may not be affected at this point, but it's something you have to watch. And this is what the cable clamp looks like. Tighten that up, You notice it's not a T-handle. It's a real ground. Tighten it up, and that baby's going to give you just what you need. Inspecting and testing. That falls under ASTM F2249. So I put it on the test because it does get involved with grounds, but it's just testing and inspecting. So the test procedures that they have don't have a set interval. My recommendation, grounds are built for personnel protection. Personnel protection should be tested every year, annually. It should be tested every year because someone's life is in risk using a bad ground. So when you inspect it, of course, look for broken ferrules or clamps, exposed, broken strands, and what happens as these strands break, you're losing ground capability. So you got to have them all. Cut or badly matched or flattened cable, that means something inside is probably broken. Extensively damaged cable covering, because that's going to allow moisture to come in and corrode the cable. Swollen cable jacket or soft spots, that means you've already got internal corrosion. And of course, if you have a clear coating, you can see dark areas. And then outside cable strands with black deposits on them. Grounding jumpers are visually defective are removed from service. Don't think that you can just bypass it. It'll be okay this time. We never use them. They never get energized. That's the time they'll be energized. They should be marked, tagged, or destroyed, or if possible, they could be repaired, but they must pass a visual and electrical test before you turn those to service. So prior to electrical testing, you want to identify the cable gauge, make an exact measurement of the cable length. And I got a diagram there to help you out. Thoroughly clean the clamp with a stiff wire brush and isopropyl. I don't even clean my feet that well. Reassemble and torque to required values. And then your maximum resistance should be calculated 1.05 RL, and you can see R's resistance per foot from the table I'm going to show you, and the cable length plus 2Y, and Y is the resistance of the clamp and ferrule assembly. It is the same for all cable sizes, times 0.6 milliohms. So this is one of the charts out of 2249. And it gives you, this is a quick chart, 2, 1, 2 aught, 4 aught resistance per foot at 5 degrees, 20 degrees, and 35 degrees. Now, if you like detail, okay. We got another table. Table 2 is a pass-fail resistance value for copper grounding jumper assemblies. And note they say assembly, not just the cable. And they have 3 values here that have this little triangle. Says this value may only be added to the full foot length measurements. So don't try to measure something that's short. That's not what you're looking for. But it gives values for your number 2, 1, 2 aught, and 4 aught cable. Very helpful for anybody testing grounds. I know a lot of you don't test them, but they should be tested. And this is a ground tester. The different manufacturers have slightly different ground testers. But the fact of the matter is that how they tell you to run the tester may be different. And here you can see they tell you to put one more or less in a loop. The other one, they tell you to tie the sides together and then make a loop. They have their own requirements for testing. So just using it is not adequate. Use it in a way that you have specified. And that, my friends, is how you ground something. Jim, you there?
I am here. Let's open it up to questions and see how things have been received on the audience side. As Jim announced during the beginning of the presentation, there will be a PDF copy of his slide deck available for download when we post the video to the website. So
Yep.
I had some requests for that. And
also, Jim, I want the paper that this is paper I designed this TP for to go out with that, because that has so much detail on personal protective grounding, it'll flood you.
all right, we will do that. I've looked through that, and that's a very useful paper, yes. So we're open to any other questions. I thought it was a very complete presentation. I was engrossed in the details myself. So here's a question from Wayne Yu. He's saying, can we measure the resistance of a TPG, but the impedance includes resistance and reactance? How do we obtain the reactance?
Well, I know AC has reactance, but if you think about it, when you test it, you're testing it with DC. And DC has no reactance. So as long as it meets the requirements of ASTM F855, which is all DC testing, you're going to be good.
Okay, and that makes sense. So the next question is, you mentioned that this is about medium voltage, but should I ask my clients at 480 volts that this is too much to expect, or do the expectations change?
No, not at all. As a matter of fact, all grounds, high voltage or low voltage, should be applied using live line tools. And the reason for that is, if you think about it, you got a handle in your hand, you go up to a 480 volt bus and you touch it and it blows up. Who do you think is going to get hurt? You know, it's something that is good, safe procedure. But the grounding between low voltage and medium, I know I said medium voltage because that's what I work a lot in, but it's also low voltage and medium voltage. Even when you go up to high voltage, it's really all the same.
All right, so the next question is, how do you size a temporary ground for a fault that lasts longer or may last longer than what the table shows?
You know what? Any fault could last longer. What if the relay doesn't work? What if they changed the transformer impedance and you didn't know it? What? So what we have to look at, if there's any concern, and there should be really no concern, all this should be done on your JHA and your work permit. All this should be laid out. But if there is any concern, don't do it. That's my advice to you. Make sure that the information that you have is accurate. If the customer cannot verify the accuracy, you're going to have to do it, which means you're going to have to walk down everything and verify that everything is going to work. Now, you can't tell if a protective relay is going to work or not. But if I were you and you were me, I think I would maybe double up on my ground just in case.
So this next question is along the same lines, but there's a slight difference, and that is he works mostly on commercial designs instead of utility. So his work is in the 600 volts or less. Does it make sense to specify ball studs for switchgear temporary grounding, or are these standards more for utility work?
Not only does it make sense, makes it easier. Those ball studs are primarily for medium voltage or lower voltages. It includes low voltage setups. And the thing is, those things go on so easy, they clamp so good, and the impedance is so low, you're going to love them. And I don't sell things. We do test and maintenance. That's what we do.
So a follow-up question, how do you size the ball studs for low voltage?
The manufacturer will help you size it according to the available short circuit. You're going to have to supply that short circuit current, but he'll help you out.
All right. So it looks like that's the end of our questions. I thought it was great material, Jim. And if any other questions come up after we kind of close out, be more than happy to follow up with an email response.
Just shoot an email to me. I'll take care of every question. Let me tell you, we have over 1,000 field service technicians, and grounding is so important to us because we work in substations, we work in manufacturing facilities, we work from 24 volts on up to 500 kV. If you don't think grounding is important, I'll tell you, buddy, it is really important. That's why I want that paper to go out to everyone.
All right. There was one more question that someone didn't quite understand. In your opinion, whether they should be using the withstand or the ultimate values from the table?
Well, see, there you go, my opinion. But my opinion is based on safety. As a member of the 70E committee, safety is always at the forefront of what I consider. And during the ASTM F855 meetings, they were very clear that the withstand rating is the rating to choose because it will not melt, short circuit will not melt the ground cable. Whereas at the ultimate, it might. So always, always, always use the withstand. Please let me be clear.
All right, I think you did it. Jim, thank you very much. We look forward to the next time you can join us. Thanks to everyone for attending today, and everyone have a good day.
Thank you, and thank everyone that attended too. Appreciate it.
So long.